Hi, I'm Greg Restall. Welcome back to week 3 of Logic, Language and Information 2. In the lessons in this week, I'm going to introduce you to proof trees for first-order predicate logic. Now, we've already seen how in first-order predicate logic we can define validity for arguments. An argument from the premises X to conclusion A is valid if and only if there's no counterexample to the argument. That is, no model where the formulas in X, they're the premises, are true and the conclusion A is false. Now, trees in predicate logic are a systematic way to try to construct a counterexample to an argument. This technique, if you like, gives us a certificate of impossibility if that search for a counterexample doesn't succeed. Now, that certificate, then, is a proof that the argument is valid since it conclusively shows that there is no counterexample to the argument. So let's look at a simple example. Consider this argument form here from the premises all F's are G's and something's not a G to the conclusion something's not an F. Think about this argument. Do you think it's valid? And if you don't think it's valid, can you describe a countermodel which shows that the premises are true and the conclusion's false? And if you do think it's valid, what could you do to demonstrate this fact? Is there a way to demonstrate the validity of the argument clearly and straightforwardly? That's what I'll show you how to do here. The argument really is valid. There's no way for the premises to be true and the conclusion false. A proof tree will provide a demonstration of this fact. And we start by writing down the premises and the negation of the conclusion here. So I've written down the two premises and the conclusion something is not F and negated it. And we'll draw out the consequences of these formulas and see what would follow if they were all true. If the argument is valid, there'll be no way for these formulas to be true together, and that's what we're going to show here. Now, of these three statements, we'll start with the second. It says that something is not G. What we'll do is we'll give one of these things a name, A. It follows then that A is not G. We're just unpacking the information that we have here, which follows from the assumptions that we've made. And we tick this formula, something's not G, with a tick here, and write an A behind it to indicate that the name A was introduced into our reasoning at this point. Now that we've been talking about an object A, we can see what else we can say about it. The first premise we wrote down tells us that all F's are G's. So in particular, this holds for the object A. So we apply that fact to A, and we conclude that if A is F, then it's G too. So we write down that conditional, FA implies GA, and also we mark that starting formula with a \A to indicate that we've applied this universal quantifier formula to the object A. Now, since the conditional FA implies GA is true, either its antecedent is false or the consequent is true. Remember, that's how material conditionals work. And so the tree splits into two cases. Either FA is false, that's the left branch, or GA is true, that's the right branch. That's the result of this conditional statement, so we tick it to indicate that it's been processed too. Now, these two cases are separate branches of the tree, representing two different possibilities. Now, this second possibility is that GA is true, but that can't work because we've already, earlier in the tree, said that GA is false. There's no way to make the formulas in the right branch true together. So we write a cross under this branch to close it, to indicate that there's no way to make all of these formulas true. Looking at the left branch, you can see that it's not yet closed. But there's one formula we haven't yet used. That's the negated existential quantifier formula, which says that nothing is not F. Now, a negated existential quantifier formula says that nothing has a particular property. Here it's not F. This acts a bit like a universal quantifier formula. If nothing has a given property, and we've got some object in mind, then we know that that object doesn't have the given property. So we can apply that fact here. Our formula tells us that nothing is not F, and we can apply that to the object A. And so this tells us that A isn't not F. So we write down not FA to say that not FA isn't true, and we write down a \A after the original formula to say that we've applied it to the object A. So we write down the not FA in the open branch, the left branch here, and not the right branch because the right branch is closed and finished. The left branch now also closes because we've had not FA and its negation not FA, and they can't be true together. So neither of these options work. The tree closes. There is no way for the starting formulas to be true. There's no way for the premises, all F's are G's and something's not a G, to be true, and the conclusion, something's not an F, to be false. It follows that the argument from all F's are G's and something isn't a G to something isn't an F is valid. Now that's just one example to give you a taste of how things go. In the next lesson, we'll take a look at all of the rules for trees for first-order predicate logic.